Hello everyone, welcome to 10-Minute Physiology. In today's video, we're going to be talking about how our eyes adapt to light levels, specifically the photoreceptor response. So with that, let's give it a go. So our eyes can operate over a wide range of ambient light levels. They can operate all the way from a pitch black room to a bright sunny day. And the range in which our eyes can effectively operate is going to be equal to 10 to the 16-fold. So in order to operate over such a wide range of ambient light levels, our eyes have to be able to adapt from going from a pitch black room to a bright sunny day, and from a bright sunny day into a pitch black room. So our eyes have to be able to adapt to changes in ambient light levels. So in order to do that, we basically have two main mechanisms. The first mechanism was the nervous system mechanism, which was the pupillary light reflex, which we already talked about. And in today's video, we're going to be talking about the photoreceptor response. So let's take a look at what the photoreceptor response looks like graphically. So the photoreceptor response graph would look something like this. So on our x-axis, we have the time in darkness, so the amount of time our eyes are exposed to darkness. And on the y-axis, we have the log of the relative light threshold. So the light threshold is going to be the amount of light that's needed in order to stimulate our rods and cones in our eyes. So what does the photoreceptor response look like graphically? Well, it would look something like this. So what we see here, our threshold to stimulate our rods and cones is going to decrease over time of exposure to darkness. And what we see here is that this graph is going to be governed by two main responses. So the cones are going to be responsible for the first portion of the photoreceptor response. So the cones are going to adapt very quickly to levels of low light. But the thing with the cones is that their threshold sort of remains high. So even though the cones adapt quickly, their threshold remains high. So it's harder to stimulate cones than it is to stimulate the rods. The second portion of the response is going to be due to the rods. So the rods are going to adapt more slowly. However, they can respond to much dimmer light because their threshold just gets so low. So now that we know what the photoreceptor response looks like graphically, let's take a closer look at the rods and cones. So remember, the two main photoreceptors in our retina are going to be the rods and cones. So this right here is a rod, and this right here is going to be a cone. Remember, the rods are responsible mainly for seeing light and dark, and the cones are responsible for seeing color. Now the rods, because they can get their threshold so low in darkness, these rods are going to be able to respond to the lowest levels of light. The cones, because their threshold sort of remains high, as we saw in that graph, they are mainly going to respond when bright stimuli appear. So what do I mean by this? Well, imagine you are in a field and it's at night. So because it's at night, the level of ambient light is going to be very low. So therefore, your rods are mainly going to be responsible for your vision, as we see right here. Now imagine fireworks are blown off in the distance. These fireworks are bright stimuli. And when these bright stimuli appear, this is going to be the cone's duty to respond to that. So the cones are going to help you to see those bright stimuli in the fireworks. So now that we know what the photoreceptor response is, let's take a look at what it looks like at the molecular level. So this right here is the outer membrane of a rod cell, and this is going to be the disc. Now inside the disc, we have a specific protein called rhodopsin. So rhodopsin, when it absorbs light, is going to undergo a conformational change, converting it into metarhodopsin 2. So metarhodopsin 2 is going to be responsible for activating transduction, a G protein. And transduction is then going to go down to the pathway. But before we talk about that pathway, I want to talk about a specific process called bleaching. Because over time, all transretinal is going to leave metarhodopsin 2. This causes metarhodopsin 2 to form into opsin. Now, when all transretinal leaves metarhodopsin 2, it is then converted into retinol. Retinol then translocates to the pigment epithelium and becomes 11-cis retinal. It then makes its way back to the outer segment, and then it recombines with opsin. So this whole process here is called bleaching. And bleaching is going to be the separation of metarrhodopsin 2 and all-trans retinal. And it basically makes the protein unresponsive to light. So in other words, it's unresponsive to light. It can't really respond to any photons coming in. So now let's talk about the rest of the pathway. So we have transducin activated. What does it do? Well, transducin is going to activate phosphodiesterase. And before we talk about that, I want to talk about what's going on in the rest of the cell. So inside the rod outer membrane, we have cyclic nucleotide gated channels. And these channels are going to be opened in response to binding to their ligand, which is going to be cyclic GMP. So cyclic GMP is made in the cytosol by this enzyme GC. So GC converts GTP into cyclic GMP. Cyclic GMP then binds to these channels, which allows them to open, and then this allows sodium and calcium to flow into the cell, which therefore allows it to depolarize. Now, this is where the transduction pathway comes in. So when transducin is activated, it activates phosphodiesterase, and phosphodiesterase takes that cyclic GMP and converts it into GMP. And when this occurs, this causes the cyclic nucleotide gated channels to close. And when this occurs, the cell hyperpolarizes and then a visual signal is produced. So activation of phosphodiesterase decreases the levels of cyclic GMP. This causes the closure of cyclic nucleotide gated channels, which therefore decreases the dark current. This causes the cell to hyperpolarize, and then neurotransmitter release is going to be decreased, and a visual stimulus is then going to be produced. So an important thing, though, that happens when these cyclic nucleotide gated channels are open is going to be the entry of calcium. And the reason why is because calcium is going to produce a negative feedback system. So calcium, first of all, is going to inhibit the GC enzyme. So in other words, it's going to decrease the amount of cyclic GMP. And at the same time, calcium is also going to stimulate phosphodiesterase, which also decreases the amount of cyclic GMP. So calcium entering into the cell is going to set up a negative feedback system. It stimulates phosphodiesterase and inhibits guanylate cyclase. Therefore, in the dark, calcium is going to prevent a runaway increase in cyclic GMP, and in the light, it's going to prevent a runaway decrease in cyclic GMP. And this particular negative feedback cycle is going to be important in the photoreceptor response. So now that we know how the cell is going to respond to light, let's talk about the photoreceptor response. So the photoreceptor response, what we're going to do is we're going to use what we learned in this video and explain what it is. So the first thing is that, remember, if we expose an eye to bright light, this is basically going to cause the rods to eventually become ineffective. And the reason why is because of bleaching. Remember that bleaching is the separation of all trans retinal from the opsin protein, which produces the opsin protein. So bleaching basically makes the protein unresponsive to light. So the CNG channels, remember, are going to close in response to bright light. The calcium entry is therefore going to be blocked, and this causes the calcium levels to fall. Now, after we return the eye to darkness, rhodopsin is going to be regenerated and slowly become sensitive to light. Because remember, the 11-cis retinal is going to come back into the outer segment and recombine with opsin, forming rhodopsin once again. So rhodopsin is going to be regenerated in the dark, and it slowly becomes sensitive to light. Now, it's important to realize that in the dark, our baseline levels of cyclic GMP are going to be relatively high. And this allows large amounts of calcium to flow into the cell. And remember, the reason why our baseline cyclic GMP levels are high is because the transducin is not going to be activated. So therefore, you have that guanylate cyclase producing cyclic GMP, and the cyclic GMP baseline levels therefore are going to be relatively high. Now, because our cyclic GMP levels are going to be high, this is going to allow large amounts of calcium to flow into the cell. However, remember that this calcium is going to have a negative feedback system. The calcium is going to inhibit guanylate cyclase and stimulate phosphodiesterase. And this basically prevents cyclic GMP from rising too high. Now in the light, so when there's a lot of background light, basically what we're going to see is a decrease in entry due to that visual transduction pathway. And this is going to stimulate the guanylyl cyclase enzyme and inhibit phosphodiesterase. This also is going to keep baseline cyclic GMP levels high by preventing it from falling too low. So in both cases, cyclic GMP baseline levels are going to be kept relatively high. And what is the importance of this? So the importance of this is as follows. By keeping the baseline cyclic GMP levels relatively high in the presence of light, this allows cyclic GMP to fall in response to further increases in light. Otherwise, the system would be saturated. So in other words, the photoreceptor adapts to the increased background light intensity and remains responsive to small changes. So I hope this video helped you understand what the photoreceptor response is, and I hope to see you in the next video. Thank you for watching, and I hope to see you next time.